Dear students, this is Dr. Rekha, Faculty of Physics from MBSR Engineering College. Today, I'll be teaching you the chapter lasers. This is the first chapter of Unit 5 of your physics syllabus. My lecture will comprise of two parts. In the first part, I'll be talking about the introduction about laser and some basics, and in the second part I will talk about the lasing action and types of laser along with the application. So this video has the first part, which is about the basics of laser. The topics covered in this are the introduction about lasers, characteristics of lasers, spontaneous and stimulated emission, and Einstein's coefficients and the relation among them. Now let me introduce you about lasers. What is a laser? Generally anyone would say laser is a type of source. Yes, but what does the laser word stand for? Actually, it is an acronym for the big word light amplification by stimulated emission of radiation. So if I take the first letter of each word of this, I get the word laser. Okay. Similarly, we also have maser, microwave amplification by stimulated emission of radiation. Nowadays, laser principle is extended up to gamma rays, hence gamma ray lasers are called grazers. The first two successful lasers developed during 1960 were ruby laser and helium neon lasers. Some lasers emit light in pulses while others emit as a continuous wave. Then we will talk about the characteristics of the lasers. What is it that makes laser superior to that of the ordinary light source? In what way is it superior? See, when we compare any other conventional light like sunlight or tube light, etc., laser exhibits few outstanding characteristics. What are the characteristics? It is they have high monochromaticity, high directionality, high intensity, high coherence. We will discuss each of them one by one in the next slides. Let me talk about high monochromaticity. What is monochromatic? It is a single wavelength. Now, if I am talking about a light source, it should have a single wavelength. It should not have a spread in the wavelength. When I talk about a laser light, the spread in the wavelength, that is delta lambda, is equal to 10 angstrom units, whereas if I take an ordinary light, the spread in the wavelength is around 1000 angstrom units, as you can see in the figure here. So this is the bandwidth of the light which the source of light has. So this narrow bandwidth of the laser light, which is around 10 angstrom unit, is called on high monochromaticity. Then what is bandwidth? It is the spread of the wavelength. You may also take frequency if you want. About the wavelength of the maximum intensity is called bandwidth. If I am talking about the frequency, then we have to talk about the frequency at maximum intensity. Then the second one, we talk about the directionality of laser. When we talk about lasers, they emit light which is highly directional as compared to the ordinary light. It is emitted as a relatively narrow beam in a specific direction. Now let us look at the two pictures. If I take an ordinary light, as shown in the first figure, the light spreads out in all directions if I take an ordinary bulb. Okay, whereas if I take a laser light, it is a highly directional beam. So it emits a narrow cone of divergence. So the directionality of a laser beam has been expressed in terms of this divergence. How much divergent it is, a light source, less is the divergence, high is the directionality. So to obtain high directionality, there should be low divergence. So if I take a laser beam the beam spread is less than 0.01 mm for every 1 meter. That means if the laser light travels for 1 meter, the spread in the beam is less than 0.01 mm. But whereas in the case of an ordinary light, for the same amount of distance traveled, that is 1 meter, the spread is around 0.5 meter. This clearly shows how directional the laser light is when compared to that of an ordinary light. Then the third one, we will talk about the intensity of the laser light. The laser light is more intense than conventional light. So the measure, how do we do it? It is with respect to the number of photons coming out from a laser per second per unit area, which is given by n is equal to P by h nu pi r square. Okay, so the intensity of a wave is the energy per unit time flowing through a unit area. This is how we measure. So the light from an ordinary source spreads out uniformly in all directions and from spherical wavefronts around it. Let me explain to you clearly. If I take an example, let us say we look at a 100-watt bulb from a distance of 30 centimeter. The power entering the eye is around 1 by 1000 of a watt. That means how much? 1 by 10, that is 0.1 of watt. But in the case of a laser light, energy is in small region of space and in a small wavelength, and hence is said to be of the great intensity. So the power range of laser is about 10 to the power minus 3 watts for gas laser and 10 to the power 9 watt for solid state laser. And let me tell you, the number of photons coming out from a laser per second per unit area is given by around 10 to the power 22 to 10 to the power 34 photons per meter square second. This is calculated using the same formula which I just stated, n is equal to P by h nu pi r square. Now we will talk about the coherent property of laser light. Lasers, the radiation coming out of lasers has high degree of coherence. Now let us discuss what is coherence. When two light rays are having same phase difference, then they are said to be coherent. It is expressed in terms of ordering of light field. Laser has high degree of ordering than other common sources. Due to its coherence only, it is possible to create high power, that is of the order of 10 to the power 12 watts in space with laser beam of 1 micrometer diameter. Now the figures show you about the incoherent and the coherent waves. You can just see the difference. In coherent, how orderly the waves are. At any given point of time, all of them are at the same state of vibration. But the same thing we don't observe in the incoherent radiation. Then we will extend this coherence to a little more bit, because when I am talking about coherence, two waves are maintaining a constant phase difference, whether we are talking about after a certain distance or after a time. So we should speak about both. So based on this, we have two types of coherence. One is spatial coherence and the second one is temporal coherence. So what is spatial coherence? The two light fields at different points in space maintain a constant phase difference over any time t. Then they are said to be spatially coherent. In helium neon gas laser, the coherence length, if I talk about LC, it is about 600 kilometer. It means over the distance of 600 kilometer, the phase difference is maintained over any time. Whereas for the ordinary sodium light, it is just about 3 centimeter. So look at the difference, 3 centimeter for the ordinary light, whereas it is 600 kilometer for the laser light. The coherence and monochromacity is related by the relation zeta is equal to delta nu by nu, which is proportional to 1 by LC. So that means it is inversely proportional to the coherence. So higher the coherence length, What do we say? Zeta is small. That means it has higher monochromacity. Okay. And the next one is the temporal coherence. What is temporal coherence? So previously we spoke with respect to distance. But here it is the correlation of the phase between the two fields at a point over a period of time we are considering. So the same example if I take for helium neon laser, it is about 10 to the power minus 3 second, whereas for the sodium it is about 10 to the power minus 10 second only. And here also we see the factor zeta is proportional to 1 by Tc, where higher is the Tc, higher is the monochromacity. Okay. Now, till now we studied about the characteristics of laser and described them in detail, how it is superior. Now let us talk about some phenomena that occur when a particle or when matter interacts with radiation. Precisely, let me take an atom in a solid. All of us know that unless until compelled, atom exists in the ground state. So let us say E1 is the ground state of the atom and E2 is the excited state of the atom. And the atom stays in the ground state as shown in figure A here. Now let us say that a photon is incident on such an atom. What is a photon? It's an energy packet. So if the energy of the photon is equal to the difference between the two energy states E2 and E1, that is H nu is equal to E2 minus E1, then our atom in the ground state will absorb this photon and get excited to E2. So it goes and sits in the energy states E2 as shown in figure B. So this transition from one energy state to another energy state, which is from lower to higher on incidenting a photon, is called induced absorption. We are inducing the atom to the higher energy state. This is also called as stimulated absorption also. Okay, so this is one phenomena we observe when we incident a photon on an atom in the ground state. So how do we define it? Light is emitted or absorbed by particles during the transitions from one energy state to another. The process of transferring a particle from ground state to higher energy state is called excitation. Then the particle is said to be excited. In absorption, suitable amount of energy is absorbed by the atoms of the ground state to get excited to the higher energy state. Then we will go to the second one, which is spontaneous emission. Now we have the atom in the excited state after absorbing the photon which is incident on it. But the atom in the excited state doesn't remain there forever. It has a lifetime. It has a life period. So after that, without the aid of any source, external source, by itself, it automatically jumps to the ground state. During this process, when it is transiting from the excited state to the ground state, it emits photon, and the emitted photon is equal to the difference between the two energy states. So the figure A represents the atom in the excited state, and figure B represents the atom transiting from E2 to E1 emitting a photon. So this phenomena where the atom is spontaneously coming down to the ground state from higher energy state to the lower energy state by emitting a photon of energy h nu is known as spontaneous emission. Then we also have one more emission which is known as stimulated emission. What happens here? See, when the atom is at the excited state, and at this point if we are incidenting a photon on it, then the atom will absorb that photon, and as a result it will come down to the ground state, releasing a photon along with the incident photon. That means during this process two photons are emitted. One is the simulated photon and the other is the incident photon. So this phenomenon, the emission of a particle from higher energy state to the lower energy state by stimulating it with another photon having energy equal to the energy difference between transition energy levels, is called stimulated emission. So you can see in the figure, the atom is in the excited state. There is a photon incident on it as shown in figure A, and after absorbing, the atom comes down to the ground state emitting two photons as in figure B. Now here we have to look into certain important features. What are they? The first one is the process of stimulated emission can be controlled from outside. Whereas spontaneous, it is very difficult to control. Here we can control so that all the photons are emitted at the same time coherently. Whereas in the spontaneous, each atom comes down by itself at its own time. The emitted photon and the incident photon have same direction, phase, frequency and plane of polarization in this case. The light produced during stimulated emission is coherent and monochromatic. Now let us compare these two, spontaneous and stimulated emissions. Spontaneous emission gives out what is known as the incoherent radiation, whereas the stimulated emission gives out coherent radiation. Just now we saw. Okay, and the intensity from a spontaneously emitted radiation is of less intensity, whereas the intensity in the case of stimulated emission is high. The light from a spontaneously emitted radiation is polychromatic. What is meant by polychromatic? Many wavelengths are there, whereas from the stimulated emission it is monochromatic. It is of single wavelength. And in spontaneous emission we see that only one photon is released, whereas in stimulated emission we see two photons are released. The light emitted from spontaneous emission has a less directionality, whereas the stimulated light has high directionality. And also the angular spread during propagation of a spontaneously emitted light is more, while the angular spread during propagation of stimulated emitted light is less. Then what are the sources that give out spontaneously emitted light? It is a light from sodium vapor lamp, mercury vapor lamp. All these give spontaneous emitted lights, whereas a laser source gives a stimulated emitted light. So different types of lasers we have: ruby laser, helium neon laser and also gas laser. Okay, so now we know that lasers are superior to that of the ordinary light due to their characteristics being like intensity, monochromaticity, okay, and high coherent, fine. And also we have understood the different phenomena that occur when matter interacts with radiation, like induced absorption, we have spontaneous emission and stimulated emission. So with this knowledge we will get into understanding what are the Einstein's coefficients and the relation between them we will derive. So we have three phenomena. One is absorption, the second one is spontaneous emission, where the atoms comes down from the excited state to the ground state emitting a photon, and the third one is the stimulated emission, where the atom in the excited state absorbs the incident photon and comes down to the ground state emitting two photons. Okay, and now we will talk about some mathematics here. So E1 is the ground state, E2 is the excited state. Okay, so that means what? E2 is greater than E1. Now let us say N1, we will denote it as the number of atoms per unit volume present at the level E1, and let us denote N2 as the number of atoms per unit volume present at the level E2. Okay, so that means what? We have two energy levels, E1 and E2 respectively. such that E2 is greater than E1, and N1 and N2 are the number of atoms per unit volume present at the levels E1 and E2 respectively. And the energy density radiation that we are incidenting on the atoms is equal to the difference between the transition levels, that is E2 minus E1, that is equal to NH nu. H nu is the energy of one single photon. So we do not know how many photons we are incidenting, so we will represent it as NH nu, where N is an integer. So this energy density we are representing it as rho nu. So rho nu represents the energy density radiation. Now we will talk about the first one, which is stimulated absorption or the induced absorption. The rate at which this absorption takes place. That means the number of atoms are transiting from energy 1 to energy 2 state. Depends on what? It depends upon the number of atoms that are present at the energy state E1 and also the energy of the incident photons. Isn't it? So that means it is proportional to the incident energy density rho nu of the radiation incident on the atom, and also proportional to N1, which is the number of atoms in the energy state E1. So if I say the stimulated absorption rate as N1 P12, 1 to 2 it is going, so I am representing it as N1 P12. It is proportional to rho nu N1. If I remove the proportionality sign, I get N1 P12 is equal to B12 rho nu N1. I will take this as equation 1. Here B12 is the proportionality constant and it is known as Einstein's coefficient of absorption, and this represents the property of energy states. Then we will go to spontaneous emission. So the atoms in the excited state come down to ground state. The rate at which they come down depends on what? On the number of atoms that are present at energy state E2. Because they are coming on their own, they don't require any external energy source. They depend only on N2 and therefore independent of the energy density rho nu. So how do we write now? N2 P21 from energy state 2 to 1 is proportional to N2. So if I remove the proportionality sign, I get N2 P21, and in brackets I am putting it as spontaneous to indicate it as spontaneous emission, is equal to A21 N2. Here A21 is the proportionality constant again, and it is known as Einstein's coefficient of spontaneous emission. So again this represents the property of energy states. Now we will go to the stimulated emission. So what is happening in the stimulated emission? Atom in the excited state absorbs the photons and then comes down to the ground state emitting photons. So here the rate at which it is transiting should be dependent on what? Dependent on the number of atoms in the energy state E2 and dependent on the incident energy density. So that means N2P21 should be proportional to rho nu, which is energy density, into N2. So if I remove the proportionality sign, N2P21 stimulated should be equal to B21 rho nu N2. Here please remember, for A21 is represented for spontaneous emission, B21 is represented as the proportionality constant representing the stimulated emission, and this proportional constant is known as Einstein's coefficient of stimulated emission. So the total transition property from state 2 to state 1 for the atoms can be written as the sum of spontaneous emission plus stimulated emission probability, right? So that means what? N2P21 is equal to N2P21 spontaneous plus N2P21 stimulated. So that should be equal to what? A21 N2 plus B21 rho nu N2. Okay, now we will look into some thermodynamics connecting this equation. Now at equilibrium temperature, so when we consider equilibrium things state, we should know that the number of atoms that are going from state 1 to state 2 should be equal to the total number of atoms transiting from state 2 to state 1 under equilibrium condition. So that means what? Upward transition should be equal to downward transition. So that means induced absorption rate should be equal to the total emission rate. So N1 P12 is equal to N2 P21. Here N2 P21 is the sum of spontaneous and stimulated emission. Please remember that. So substituting equation 1 and equation 4. Equation 1 represents the transition probability rate for absorption, whereas equation 4 represents the transition probability, total transition probability, which is the sum of spontaneous and stimulated emission. So what do I write? B12 rho nu N1 is equal to A21 N2 plus B21 rho nu N2. So here what am I doing is, I keep A21 N2 as it is. I bring B21 rho nu N2 to the other side. So what do I get? A21 N2 is equal to rho nu, I am taking it as common, into B12 N1 minus B21 N2. So from here rho nu is equal to N2 A21 by B12 N1 minus B21 N2. So here what I am doing is N2 A21 by, I will take out N2 B21 outside, then it would be N2 B21 into B12 N1 by B21 N2 minus 1 in the denominator. So this finally gives me what? Rho nu is equal to A21 by B21. I am taking the B21 in the denominator to the numerator and N2 is getting cancelled. So we get rho nu is equal to A21 by B21 whole by B12 N1 minus B21 N2 minus 1. Let us say this equation as 5. Then we will go to Boltzmann distribution law from thermodynamics. When I am taking that law, according to that law, the distribution of atoms among the different energy levels at thermal equilibrium temperature T, we write it as, if it is an energy level E1, then we write it as N1 is equal to N0 e to the power minus E1 by kT. And for energy level E2, we say N2 is equal to N0 e to the power minus E2 by kT. Here N0 is the population or the number of atoms in the ground state and K is the Boltzmann constant. Now I have these two equations N1 and N2 at E1 and E2. So if I take N1 by N2, then N1 by N2 is equal to what from these two equations? E to the power E2 minus E1 by kT. So when minus E2 goes to the numerator, I get plus E2. So please remember that, and we know E2 minus E1 is equal to H nu. So substituting for that, we get N1 by N2 is equal to e to the power H nu by kT. And in equations 5 we have what? Rho nu is equal to A21 by B21 whole divided by B12 N1 by B21 N2 minus 1. So this N1, so substituting equation 6 in equation 5 for N1 by N2, we have rho nu is equal to A21 by B21 whole divided by B1 by B21 e to the power H nu by kT minus 1. Okay, let us say this as equation 7. According to Planck's law, we will go to the Planck's radiation law. The expression for the energy density of radiation is given by what? Rho nu is equal to 8 pi h nu cube by c cube into 1 by e to the power h nu by kT minus 1. Let us say this as equation 8. Here h represents Planck's constant, nu is the frequency of radiation, c is the velocity of light, k is the Boltzmann constant, t is the temperature. So Planck's radiation law states this expression for the energy density, and equation 7 we have got it from our concept. So anyway both these things should match. So comparing this equation 7 and 8, what do we get? In the denominator B12 by B21 is equal to 1, and in the numerator we see that A21 by B21 equals 8 pi h nu cube by c cube. Here B12 is the Einstein's coefficient of stimulated absorption, B21 is the Einstein's coefficient of stimulated emission, and A21 is the Einstein's coefficient of spontaneous emission. So these equations 9 and 10 gives the relation among these Einstein's coefficients. So equation 9 and 10 represents the Einstein's coefficients and the relation among them. So what do we conclude here? From equation 10, A21 by B21 is proportional to nu cube, that is the ratio of Einstein's coefficient of spontaneous emission to stimulated emission is directly proportional to cube of the frequency of incident photon. And the rate of spontaneous emission increases rapidly with the energy difference between the two states. From equation 9 we have B12 is equal to B21, that is thermodynamically it was proved by Einstein that the probability of stimulated emission and absorption are equal. And please note that the equation shows the ratio of spontaneous emission rate to stimulated emission rate. So this completes the part 1 of lasers. Here we stop, and in the next lecture I will be teaching you about the principles of lasing action, types of lasers and the application. For any queries you can contact either me or your concerned faculty. Thank you.